Because the world is not only made of single-up joints, we finish the section on joint design by talking about other types of joints, like T-joints, for example. So let's go to the last module of joint design. So far, we have discussed basically one type of joint, the single-up joint. But in real life, that's not the only joint used. So in this module, I want to talk about other types of joint, tubular joints, T-joints, and corner joints. Let's start with the tubular joints that you would see in bars or in tubes, tubular joints. You have several configurations here, and if you think a bit about all of them, you will see that they all have the same principle that we actually applied in the single-up joint. We want to make sure that we reduce at maximum the peel stresses and we increase the shear stress component over a large bonded area. This principle applies to any kind of joint. In some of them it's very obvious. For example, here you have a joint where you have a huge shear stress area when you load the joint like this or the joint like this. Another configuration here, it's even better because you don't have that part, the external part that is not nice. The problem is some configurations, of course, they are ideal and they would work fantastically well, but in terms of production, this is arguable. Obviously, this is much simpler to apply. But again, whether you have bars or tubes, I remind you this rule of thumb: make sure that you increase at maximum the bonded area loaded in shear and you reduce the peel stress. About T-joints, it's about a bit more complicated for the adhesive, because naturally if you apply this kind of loading, it will fail at a very low load, the adhesive, because the peel is enormous. But we can use these gussets or reinforcements to reduce the problem of peel. Let me show you one joint, a T-joint made of wood. Okay, we have a project at the moment where we are using wood material in a car structure, and inevitably we have this type of joints. So this is a simple T-joint. If it's loaded like this, for example, this would not be good because it would load the adhesive a lot in peel. So we could place here a reinforcement in this place. Again, philosophy is the same. When you have problems of peel, you reduce that by adding shear stress component. Let me comment on a work that we did in the past. You have several joint configurations. Here we are talking about T-joints, some very simple, others with reinforcement on both sides. And for the base, we initially used 1.5 millimeter thick. The rest is all 1.5, but initially for the base we use 1.5, and these are the values we obtain. There is obviously an increase. The loading is in this direction, by the way, for all of them, okay? And there is an improvement because we are reinforcement as we go in this direction. But we were really surprised when we went from 1.5 to 10 millimeters. We had nearly one order of magnitude increase. And this is related to the way the joint failed. When you have a thin base, you have plastic deformation of the thin base, and this is what controls failure, not the adhesive, the plastic deformation of the base. When you use a thick base, then the adhesive can work in peace, and you have all this bonded area that will work in shear, and this gives you a much improved joint strength. Actually, you go from in this case, for example, 1 up to 10, one order of magnitude. So really, the yielding of the metal can be a big limitation. This is the case of a T-joint. In the case of the single-up joint, you already know the story. In the case of corner joints, it's something very similar to the case of T-joints. Again, if you have problems of peel, you would use reinforcement to make sure that the adhesive is loaded in shear. So in this module, we have seen other type of joints, T-joints, corner joints, but the philosophy is the same. And if you have another type of joint, the philosophy will be the same. Make sure you reduce peel at maximum and increase the shear stress component that will load the adhesive over a larger area.